doing problem 1 from section 4.4. This is just more kind of examples of what we had just done in the example 1. So again, well, maybe go through this a little bit faster. It says find the derivative of each function. So we've got 4 to the power of 3x. So its derivative dy dx, according to the rules that we were just looking at in that example. Just since this is a base other than e, the first thing we're going to want to put is the natural log of that base. Then we just copy the function, 4 to the power of 3x. And then we look up in the exponent, we see what that is. We multiply by its derivative. So we get, that's a 3. So that's perfectly fine way to leave it, or you can put the constant in front. So 3 ln 4, and then 4 to the power of 3x. So that's part A. Then part B, we got z is equal to, try to squeeze all of these on the same screen. I'm not sure I'll be able to. E to the 7, t to the third plus 5. 7t to the third plus 5. Okay, so again, let's get our notation correct. This is z. T is the independent variable here, so the derivative is called dz dt in Leibniz notation. Okay, so again, this is a base e, so we don't have to worry about that ln part. We just, first thing we'll do is just copy the whole thing. 7t to the third plus 5. We just multiply this by the derivative of what's up here in the exponent. So we get 21t squared. Derivative of 5 is 0. Let's go ahead and put the constant and the t term in front, so we get that times e to the power of 7t to the third plus 5. Okay, for part C, we get another exponential function, y is equal to 15e to the 5x squared. Okay, so again, y is a function of x here. The derivative here is called dy dx. And we've got basically the first thing we'll do here is just copy the whole thing again because it's just base e. And then we just multiply by the derivative of what's up there. That's 10x. Now we've got a constant times another constant. We'll go ahead and combine those, put the x in front. We get 150x e to the power of 5x squared. Okay, then another one that's kind of similar to the one we saw in the example. Q is equal to 3 times 5 to the power of 1 over s. That's an s squared. Okay, so again, you definitely do not want to multiply the 3 and the 5. I explained that in the example problem. But let's go ahead and rewrite the function a little bit before we take its derivative. If I've got that, it's 1 over s squared, I'm just going to rewrite that as s to the power of negative 2 instead of having 1 over s squared. So now we'll take the derivative, and again, q is the dependent variable, s is the independent variable, so this derivative is called dq ds. Okay, and then again, the idea here is we look at the base. The base is 5, it's not e, so we're definitely going to want to write that ln 5 first. Then just copy the whole function, so we get 3 times 5s to the minus 2. And then I want to take the derivative of the thing that's up there in the exponent. So that's going to be negative 2s to the negative 3. Okay? So that's the final answer there, but we'll go ahead and simplify that a little bit. So we're going to get, I'll put the negative 2 in front, and we can multiply it by that 3 that we have there, so that's going to give us minus 6. That s is to a negative power, so I'm going to move it to the denominator. So what we're going to get after all that, we'll have minus 6. The ln 5 is still there. And then we've got this, I combined the 3 and the 2, so that 3 is not there anymore. I got 5 to the power of s to the minus 2, so times, I'm going to go ahead and rewrite that the way it was before, 1 over s squared And then in the denominator, that's s to the negative 3. If I move it down, it becomes s to the positive 3. So there's our derivative there. And based on what we have left here, I think I'm going to go ahead and put the last two on a different video, since I don't want to run out of room and those ones are a little bit longer. So stay tuned, next video for the rest of them.